Good morning, everybody. Before I start, I'd like to thank the University of Northampton and Stefan in particular for the opportunity to be here. And again, there's a few mathematical calculations in this, so hopefully I don't look around and see a few heads falling down and going to sleep. So I'll continue. So in the contents section then, the Annex N safety factor equation for the minimum safety factor used. There were 4 case studies done with similar characteristics. In my time, I saw these, after spending a long time in the company, I saw these lifts over time and noticed there was some life differences between the lifts. So the cases studied are from knowledge of the sites that are contained in the portfolio. And what I'm going to compare them with is an equation that's used in the wider industry, which is not just for lifts, for running ropes over sheaves, which are used to assess what's called the bending cycle, or bending cycles that the lift can perform. Okay, so the findings after the equation for Annex N safety factor and running ropes over sheaves, separate equations, are assessed and compared for rope life. So after that, there's some cost implication for one of the case studies to alter the system parameters and assess the life cycle and the benefits of changing the parameters of the system. And to conclude, should life of ropes be taken into consideration in high-use lifts? And after that, there's some further work performed for studying suspension ropes, and the possibility of some changes to Annex N equation is discussed, if you like. So, okay. So the Annex N safety factor equation, which a lot of you will be familiar with, I won't go into it in big detail, but it's contained in Annex N, and by calculating that equation out, you get a minimum safety factor that you must apply to that particular system of lift. So the safety factor equation was derived from work by Professor Kay Fodder of Stuttgart University and Sen prior to the introduction of EN 81 to create this equation. So a work by an author called Berner states that the equation is actually based on fibre core ropes and is, again, it's not actually meant for every type of rope. So it takes into consideration, as you can see there, the traction sheave groove type, the amount of diverter pulleys, the ratio of the traction sheave to diverter pulleys, the diameter of the traction sheave, and compares that to the rope itself. So by calculating that out, you get a particular number. So when the minimum safety factor is completed, it will give a minimum predicted number of bending cycles of 600,000 before the rope becomes at the discard point. So that's a kind of a typical configuration of the lifts that I was actually looking at. Where they were all bottom drive, 2-to-1 configuration. So that just gives you the idea of the amount of pulleys that would be in the system of that type of lift. So the case studies, 4 cases were examined where rope renewal had occurred at various times between 3.5 and 11 years. They're all, again, 2-to-1 suspension ropes with a traction sheave at the lowest level, and therefore they all had similar parameters. They're all high usage lifts and are contained in either office or shopping centre applications. And each case had the following performed to assess the safety factor and the bending cycles of the system. So what I actually did was calculation of each lift for the minimum required safety factor for each lift, then calculated from the system parameters what the actual safety factor for those lifts were. And then separate calculations again were used for the running ropes over sheaves, which are used in the wider rope industries to calculate, again, how many bending cycles that lift could perform. So again, Professor Fodder, he developed an equation for bending cycles for running ropes over sheaves until what's called the discard point, when the rope should be changed. And this is the equation. It's quite a long-winded equation there, but the basis of the equation is it takes into consideration the dynamic tension of the rope and the force factors underneath, which means we take into consideration the guidance factor, are we using shoes or sliding shoes, the rope efficiency factor, the factors for parallel arrangements, that talks about more than one rope, so there's 2 ropes, 3 ropes, 4 ropes. And then obviously when we accelerate the lift, we actually create another tension in the rope. There are constants, which are detailed there, which are contained in FIRA for different types of ropes, which are put into the equation for that type of rope. And again, we take the traction sheave diameter and the rope length diameter, and then we calculate the length of the most stressed part of the rope. That is the piece of rope that actually goes round the sheave, more round the traction sheave, and more pulleys than any other part of the rope. That's a defined length. Okay. So once we actually equate the bending cycles, we then have to put in what's called correction factors. These correction factors are the ropes well lubricated? And for brand new ropes, we take that as 1. So in the equation, it doesn't have any effect. But it is possible for poor ropes, after a period of time, to become in poor condition, for that value to go down to 0.2, so you can see how the effect of the rope can deteriorate in terms of life. So the type of construction of the ropes, are we using fibre core, 6-core, 8-core, independent wire rope core? And the traction sheave groove type, so are we using what type of groove are we using, V, U, or undercut U? So, and then are the ropes without skew, which shouldn't be a problem in lifts because we should be actually moving from one sheave to the other without actually entering the next pulley at an angle. We should be coming directly into the next groove. So when we've corrected the bending cycles, calculating the trips, we have to work out how many round trips we do. So that a trip from the bottom and then to the top and then back again. So that's done by calculating, as you can see below. So the reason why you have N core P and N core T is the pulleys are always U groove, which has a different calculation. So we take out the FN3 portion of it and apply a different number. And from that, we get a number of bending cycles, number of round trips that lift will actually be able to do. So, and then one more calculation has to be done. And by using a factor called the Holchak factor, this is a gentleman who studied lifts and how many times a lift would actually, how many journeys it would make on a round trip. So as you can appreciate, a lift will go from the ground or the main stop to a high level, but it may stop a number of times on the way up and a number of times on the way down. So we actually use this equation then to actually find out how many actual journeys we expect that set of ropes to be able to make before it's discarded. So again, an expected system number of trip counter journeys can be, by the lift, can be pre-calculated. Okay. So the case study findings. Sorry. So case study findings, a bit of a table here, so I'll just go through it. So 4 cases there. So on the left, I have a minimum safety factor calculated on the left in the C1 line, and then the actual safety factor was calculated for that system. So all the lifts actually met EN81. The bending cycles that were corrected, so that's the corrected bending cycles expected. And then the trips, which are the round trips to and from the main stop to the highest level and down again. So when we've calculated on C4 there, how many actual journeys we expect that lift to make before the lift becomes discarded. And on C5 column, that was the actual trip counter that was read on site. And C6 shows the difference between the actual C4 and C5, the measured and the actual values that occurred. And the actual time on the end was when the ropes were actually exchanged on these lifts. So what that means is in C1, the safety factor is above the minimum calculated, so all Annex N is achieved. In C2, the bending cycles exceeds the 600,000 figure that was designed into EN81, so they've all exceeded that. And in C4, the number of round trips expected to be performed before the discard point is shown. So again, in the C5 value, which is in the actual trip counter, is higher than those recorded in C4, which was the expected time when they should have been changed. And C7 shows the actual periods when they were changed. So the trips according to C4 in all cases had exceeded the maximum usage time and deteriorated beyond the discard point, which means the inspection regime did not capture the rope exchange period when they should have been done. So the case study findings. So exchange of ropes to fire a calculation C4 would have meant earlier replacement. So on that table, if we had changed them when they should have been changed, we should have been changing the ropes at these periods rather than when they were changed. As you can see, the numbers are considerably less. And in case study 1, we're under 2 years. That's how much operations that lift was doing. So then looked at a case study 1, which was the worst case, and cost to value over a 20-year period. So again, the trips in C4, when they should have been changed with the system parameters that are there, of 353,000. So after system parameters, by increasing the traction, diameter traction sheave from 400 to 480 and increasing the ropes from 5 to 6, what difference did that make? So as you can see there on the existing scenario on the first line talks about 353,000, and by changing 2 parameters, we've actually increased the actual journeys that those set of ropes can make significantly. So an initial increase of 20% with a number of expected trips was actually raised by 345%. So that means we've increased the life from the current 3.5 years as they were changed to 10 years. So the cost of changing these parameters. So in scenario 1, that's how much it would cost with the expected 5 rope change periods over that 20 years. And the cost of actually purchasing the ropes and actually the labour to do the job ends up being over €40,000. With the system parameters, we've added €910 to the beginning of the investment in the job. It's cost us a little bit more because there's more ropes, but the cost of changing shouldn't be any different. But now we've actually only have 1 exchanges over that period of time, which means now we're going to spend considerably less by just changing the initial system parameters. So significant life cycle saving from minimum initial investment. And the conclusion will be common for MRL lifts to have a reeving ratio of 2:1 or 4:1, which you have on larger low capacity lifts. That means we will have more bending cycles per round trip on higher reeving ratio lifts. With the 600,000 bending cycles achieved sooner, as each round trip will mean that the rope will reach the discard point in terms of time much sooner. So the safety factor equation, as stated earlier, is based on fibre core ropes, according to the author Berner, when lifts were predominantly 1:1. So it's now desirable, again with machine roomless, for space saving within a building to have a minimum 40:1 diameter of traction sheave to suspension rope, which is the minimum you're allowed in the N81. So the choice of traction sheave groove and the traction rope to ratio and the static and dynamic tensions have a major effect on the number of bending cycles and therefore the rope life. So for high usage lifts, the rope life should be considered. Okay, so some further work that was looked at was the Annex N safety factor equation by Berner, again, was designed for fibre core ropes. So after looking at the author Fira, he has a book there which we go through, and we look at table 3.14b. We can see in the Annex N safety factor equation, the B2 and B4 values are replicated in the safety factor equation. So because we also commonly use IWRC ropes, now commonly used on lifts, these have a different B2 to B4 value. So just some quick calculations on that. If substituted directly, now that would further work would have to be done on this, then it would increase the safety factor by 8% for an independent wire rope core than a fibre core. So, and again, that was done on calculations for case studies 1 and 4 where IWRC ropes were used. So again, further work is required to have a safety factor equation that can take all types of steel wire suspension rope to be calculated. So thank you for your attention.